just doesn't say anything for some reason. Okay. Hey, we have 6 people. All right. Okay, so the question was, how many chapters do we have left? And if we look at the syllabus down here, today is the 23rd. We start 16. We do that two classes of that. We have guards. These are not actually chapters. These are other things. Oh, come on. Guardian. Then we have another chapter on transactional memory. And then we have an additional lesson on something called Paxos. So while there are like 5 more subjects, there's only 2 actual chapters.
It looks like your syllabus teaches through Thanksgiving break.
No, this isn't oh, you're right. It does. Thanksgiving break is. Why is it doing that? But you must be right. Oh no, Thanksgiving break is here. 26, 27, and 28. And then 25th, we have class. Yay. Yes, the last 2 are review. So, all right, all is right with the world. Let's go to chapter 16. Are there questions? Anything? Just anything. I could do that if you'd like.
Nice.
Okay.
I was slightly off on my answers for the lazy one.
Uh-huh.
Like I did pred.next equals cur instead of cur.next, and all of mine were just so close, but just a little bit off.
Oh, I'm sorry. All right. So we have so the remove method for the lazy method, there should have been 2 things from that list. There was cur.marked equals true and pred.next equals cur.next. Those are the 2 things you should have checked. And as I say, it doesn't matter what order they're in, of course. You can do it whatever way you want. Lazy, of course, doesn't have atomics in it because lazy is using locks. And which goes with which. Come on, you can move. Why is my computer slow? All right. So the simplest set is the coarse grain set, right? 1 lock to rule them all. Hand over hand locking is a description of the fine grain set. And traverse the list twice. That's what we do with the optimistic set, right? And has a Boolean mark field. That's the lazy set. The lock freeze set does not have a mark field. It has an atomic markable reference. Clean while traversing. That's what the find method does in the window class of the lock free set.
So lock free and course free.
Or well. Okay, so that's the quiz. Any questions? Yes, Baron.
Question with the code again.
Yep. So, I mean, this is something that you can just simply look up, right? What is wrong with my computer?
This is a YAML file. YML.
Yet another markup language. It stands for, and it's just a standard markup language that you can use for things, and that's what I write the quizzes in. Okay, so the remove method, right? The 2 lines that are missing were cur.marked equal true and pred.next equal cur.next, right? So cur.marked is the logical remove, and the pred.next equals cur.next is the physical remove. Okay? All right.
Copy.
Because pred.next already equals cur. That's the concept of pred and cur. Make sense? Yep. All right. Slideshow. Future scheduling and work distribution. Cool stuff. You should be excited just to be here. My gosh, what is going on with my computer? All right. Okay, so how to write parallel applications. How do you split a program into parts in an effective way and manage threads? Suppose you're doing matrix multiplication. Matrix multiplication looks like that, right? So we're iterating over K in the summation. And the code would look something like this. So we have a thread. Threads have, so that we see extends thread in the top there, right? And then we have which matrix entry to compute. So the row and the column we want to compute. And then the actual computation down here is this dot product. It's we're going to sum over all the i's, row I times bi col, right? And then we're going to set c row col equal to this dot product. And you can imagine the full multiply method looks like this, where we create n by n workers, and then we start them, and then we join them. And what's wrong with this, right? Well, threads require resources, memory for stacks, setup and tear down, scheduler overhead. It's worse for short-lived threads. So we have thread pools, the concept of thread pools. It makes more sense to keep a pool of long-lived threads around to do work. Threads are assigned short-lived tasks. They run the task, then they rejoin the pool and wait for the next assignment. And this is an abstraction, right? It insulates the programmer from the platform. A big machine has a big pool and a small machine has a small pool. And that creates more portable code. It runs well on any platform. You don't have to mix the algorithm platform and platform concerns. So in this context, we have a thing called an executor service, which takes a task, which is described by a runnable object. Runnable is an interface that has a single method on it, void run. And then there's a callable, which has a call and returns something of type T. And then there's a concept of a future. Now, a future is a really cool thing. It's one of the more important things for you to take away from the course. If you haven't heard of it already, a future is a proxy for a value that is yet to be computed. So when I say executor.submit task, thank you. Side digression. I was a graduate student. Stop me if you've heard it before. I was a graduate student. I was sitting in the office and there was this Korean student in there with me and he sneezed. And I said, God bless you. And he like does this and he pushes himself away from his desk and he's looking around the room like, you know, what's going on? And he looks at me and very solemnly he says, God bless you too. So I told him that's what we say when someone sneezes, you know. Anyway, so the idea is I take this task, and this task describes a way to compute something of type T. And what I do is I submit this task to the executor, and I get back a future, and I get that future back immediately. The task doesn't run immediately, but I get the future back immediately. Say the task takes an hour to compute. The next millisecond, I get the result back as the future. And that future doesn't really have a value of type T in it at first, but eventually, when the task completes, it will get stored there, so I can go back and look for it. If I call future.get, that will block until the future is ready. So the idea is I can do things in parallel by first submitting a task, then doing some other work, and then calling future.get. And this other work here will overlap with the computation of that value t in task. Reagan, you look slightly unhappy.
It's making more sense as we go.
Okay.
JavaScript reporting.
Yes.
Have you ever sent me a CAR request and did it asynchronously?
Probably not in a very long time.
All right. So yeah, this paradigm is used in a lot of places. Okay. So submitting a runnable task returns a future. Also, you can submit that as well, but that doesn't have a value. And the get method blocks until the computation is complete regardless. So executor service submissions are like New England traffic signs. They are purely advisory in nature. The executor, like the New England driver, is free to ignore any such advice and could execute all the tasks sequentially if it so chose. Right? It's going to do whatever it does. So we can think about matrix addition and how we might speed that up. Now, we don't want to run every element of the matrix in parallel necessarily, but what we could do is we could, divide and conquer, right? That's a standard way to parallelize things. And if you've got a matrix, the way to divide it is to divide it in four. So if I take if I take this side of the matrix and I divide it into four submatrices and this side into four matrices, this is how I would do the addition. So I have four parallel additions that I could do to solve this problem. And so this isn't quite real Java code. It has subscripts and whatnot. But the base case is to add directly. So what we're going to do is if the dimensions of our array are 1, then we have the base case, and we're just going to add whatever element we've got. Otherwise, we're going to partition A and B into half-size matrices AI and BJ, AIJ and BIJ, and then we're going to do the four parallel additions, and then we can call get on all four of those things so that they can finish. And the matrix example is not typical. The tasks are completely independent, and one result does not need the results of another to complete. Often tasks are not so independent. There is Fibonacci, which you all know and love dearly as computer scientists, and it works like this, right? And you can, even though it's the least efficient way to compute Fibonacci, we can use this recursion formula, and we can use this as a source of parallel work, right? Not just ordinary work, we can make parallel work out of it. And so this is obviously very inefficient, and you wouldn't really, if you really need Fibonacci numbers, this is not the way to get them, right? Use the exact formula that that looks like this. Okay, this is Python, but this is the exact formula. So it's based on the golden ratio, and it's just magical. Okay, so back to parallelism. So the way we do our Fibonacci is we have parallel calls. We have two parallel calls for the left and right portion of our tree, arg-1 and arg-2. And then we do the sum of the gets, and that's the result. And, if the base case, we have a 1. Okay, and this is a multi-threaded program, is a directed acyclic graph, or DAG, and it unfolds dynamically, and each node is a single unit of work. And if you were to sort of draw it in a picture form, it would look kind of like this. So, each Fibonacci computes its two subnodes and then returns the result, right? And if you want to think about each of these circles as a unit of work in the Fibonacci calculation, and the arrows represent the dependencies, right? Fib4 is going to call Fib3, and so on. You want to know how parallel is that, right? And so you have total work, which is the total time on one processor, and then you have the critical path length, which is the longest dependency path, and you can't go faster than that, right? So in this case, you want to look at this picture, and there are 17 circles in this graph, right? And so that means the amount of work is 17. However, the critical path is different. if I were to try to draw a path through these things, the longest path is 8. Okay. So that would be the fastest. So there's 17 units of work here, if you want to think of it that way. And the fastest we can do them is 8, right? So TP is the time on P processors, T1 is the time on one processor, and T infinity is the critical path length. That's the time on infinity processors, right? So you can say T parallel is greater than or equal to T1 over P, and TP is greater than or equal to T infinity, right? And your speed up is going to be T1 over TP. We've seen that before. And if you have T1 over TP is proportional to P, then you have linear speed up. And the maximum speed up you can ever get is T1 over T infinity. So in the case of our Fibonacci problem that we just saw, what is the maximum possible speed up we could get? What did we say T1 was? 17. What did we say T infinity was? So the maximum speed up we can get is 17 over 8. See, and I can ask you like a nice little quiz problem. I can show you a graph. I can say, what's this maximum speed up you can get from executing this graph?
So P1 is like however many there are.
Yes. T infinity. It's the longest critical path, yeah. The longest path of dependencies that you must go through, right? That you can't do in parallel. So let's look at our matrix addition again. We have 4 parallel additions. Let A P of n be the running time for an n by n matrix on P processors. And so A1 n is the work and A infinity is the critical path length. So the amount of work is going to be 4 times the work on a half size problem, right? Plus some additional stuff. So that's of order 1. And that gives you order n squared by the master theorem, which you will encounter. If you have not encountered it before, you will encounter it many times in your courses in computer science. And you can sort of verify it like by just substituting an n squared in there. Okay. And the critical path length is going to look like this. It's going to be a infinity of n is just going to be equal to one of these paths because all 4 can go in parallel, right? Plus, again, some critical part of it. And so what that's going to do is that's going to give you log n. So, and you can verify that and shoot. Hold on. I want to fix that. Come on. There we go. I forgot my mouse today. I got to use this stupid touchpad. All right. All right. So what's the fastest we can do matrix addition? What's the big O behavior for doing speed up for matrix addition?
Log n.
So what's T1? T1 is order what?
N squared.
And what's T infinity? So n squared over log n is the speed up maximum speed up you can get for matrix addition. Okay, as you get larger. If you're parallelizing in this way, right? And you just scale that up with the processor. Okay. And for matrix multiplication, right? It's going to look like this. And that's going to look like this. It's 8 multiplications and 4 additions. And so the amount of work for multiplication is going to be 8 times the half size thing plus the addition, right? So that works out to be order n cubed, which you can then, also verify. And then the M infinity is going to work similarly. We're going to have M infinity equals M infinity n over 2 plus A infinity of n, because it's got to have the additions. And that becomes log squared n. And that checks. And so the parallelism for matrix multiplication goes as order n cubed over log squared of n. And so if you multiply two 1,000 by 1,000 matrices, that winds up being something like this. It gives you a parallelism speed up of 10 to the 7. And the original slides said more than the number of processors on any real machine, but time has gone by. 10 to the 7 processors used to sound like an outrageously big number, but Fugaku, which is I think like the, I don't know, sixth fastest machine in the world, already has 7 million, right? So I don't think that anybody's really going to multiply 1,000 by 1,000 matrix on that machine, but in principle, right, you have that many cores. So parallel applications. So the way we want to do things is parallel applications don't have direct access to the hardware processors, right? I mean, they kind of do now. You can do what's called pinning, but basically you don't want to worry about those low-level details if you don't have to. You just want to have a mix of jobs, and you want them to all run together and come and go dynamically and make the best use of the machine. And the way this works is something like this. We have, tasks which are runnables and callables, and we have a user level scheduler. We have some kind of thread pool there, and that sits on top of the processors. That's sort of what we want to imagine. And the thread pool, we want to match the number of threads to the number of hardware processes that we have, so that we can have them, remain fixed to those cores. And we don't have things scheduling in and out all the time if we don't have to. So initially, we will have all P processors available for an application. And some serial computation can take over one processor, leaving P-1 for other work, like waiting for I/O or whatever. So what we want to do is map our work onto P processes, and so that we can get a P-fold speed up if possible. If the kernel lets us. And okay. So let's see how we do this. We've got a bunch of different thread pools, workers in our thread pools, right? And they're each trying to do work. And I think these look like donuts. You could call them tires, I guess. But I think they look like donuts, and I envision the work as the CPU bugs eating the donuts. Yes, yes. They also resemble those plastic rings. Okay. Okay, and so there's work distribution. You can have work dealing. You can have one processor deal out the donuts to the others. But it's hard to get these balances to work. There's also work stealing, right? So if one process runs out of work, it can go hunting among the other ones for work to take. And what we want to look at is the concept of lock-free work stealing. So each thread has a pool of ready work, and you can remove work without and it can remove its own work without synchronizing. But if you run out of work, you steal someone else's, and you choose your victim at random. So this looks like this. Each of the workers has a double-ended queue. And there are push bottom and pop bottom that each worker uses exclusively on its own. And then when it runs out and it has to obtain work, well, when it wants to put work on, it pushes from the bottom. But when it runs empty, it's going to reach over and take something from the top. So we're going to have a pop top method. And so that we want on our deck, we want 3 methods: push bottom, pop bottom, and pop top. And the first 2, push bottom and pop bottom, never happen concurrently. And so, there's only the one that the thread that owns that queue is the one that's going to use those 2 methods. And if you're going to someone else's queue, you're only using pop top. So Since these are the most so that these push and pop bottom are the most common, we want to make them fast and minimize the use of CAS, right? So ideal is weight-free, linearizable, constant time. And the pop top may fail if there's two threads trying to steal from the same one, or if a pop bottom and a pop top are fighting for the last unit of work. So here is what we call the dreaded ABA problem, right? We know that we want to get the unit of work that's at 3, and we check. We say 3 is the one we think we want, and then when we go to but in between when we identify the one that we want to take out and when we take it out, it could be that we have a completely different set of tasks in there. So this one thought it wanted 3, but something else took 3 and ran it in the meantime after it identified it. And if it just checks and says there were 3 units in the queue beforehand and there's 3 units now, then I'm good. Then it doesn't work. That's what the ABA problem stands for. The ABA problem means that, it used to be A, it became B, it became A again, and you think nothing has changed. You see the same value and you think nothing has changed. That's the essence of the ABA problem. And so what we're going to do to fix that is we're going to put a timestamp on everything so that we can't ever look the same if we put work in there. And what we're going to use is what's called an atomic stamped reference. So we had an atomic markable reference, which had a bit. This one is going to have an extra integer. And the index and the stamp are synchronized together. So the way we're going to do our queue, the top is going to be this atomic stamped reference type. The bottom is just going to be a volatile int. And then the tasks are going to be in this runnable array. Okay, so here is our class BDEQ. And we have our push bottom method. And our push bottom method is very simple. Okay, the bottom is, and you think of these indexes as going down, right? So they start from 0 and as they get larger, they go down. And to put something into the queue, I assign R to task's bottom, and then I increment the bottom of the queue, right? So if at this point, well, remember that in Java, the way we do things is bottom, it's not supposed to be a valid value at bottom. The valid values are from top to bottom -1, right? Just like the size of an array. If you get a size of an array is 10, valid indexes are 0 to 9. So in this queue, the valid indices are from top to bottom -1, right? So what I do is first I fill in this value, this runnable task at the end of the array, or past the end of the array, really, past the logical end. And then I increment bottom next so that other threads now that potentially could steal this work, they can now tell that there's something in that slot. Okay, so I need to do it in that order, right? First, I put the thing in there and then I increment it. And it needs to be volatile so that order is respected by the compiler. Okay. So that's all there is to push bottom. Now, pop top is a little more complicated. So first thing we're going to do is we're going to read the old top and the old stamp, and we're going to get those values, right? So that we're doing the same thing we did before, right? Where we have an array of size 1 of integers to get the stamp because Java can only have one return value. And then we're going to compute some new values. So the new top is going to be old top +1 because when I'm taking stuff from the top, I need to increment the top. And the new stamp is going to be the old stamp +1. So whatever the stamp is, we're going to keep it incrementing. And that will prevent duplicates and it will avoid our ABA problem. So if the bottom is less than or equal to the old top, that means that there's no work in the queue and there's nothing to steal. And so I just return null. So pop top fails by returning null, if you will. On the other hand, if if there's work in here, then what happens is I take the runnable task that's at old top, and then I attempt to cast old top, new top to old stamp, new stamp, right? And if I do that and I succeed, then the task is mine and I run it. And if it's not, I return a null. And pop bottom, on the other hand, is going to work as follows. If the bottom is 0, there's no work, I'm going to return none. Otherwise, I'm going to decrement the bottom and then remove the task. So if I decrement the bottom, that means that no longer can anyone else see that bottom task. And now I'm going to capture that task in runnable R. Again, I'm going to get the stamp and all this other stuff and the old top and the new top. And if the bottom is greater than the old top, then I can just return it because I know that nothing has pushed the old top to the point where it took my last unit of work, right? So I don't need to do any synchronization in that case. On the other hand, if the bottom is equal to the old top, then I'm potentially fighting with someone for the last unit of work. And so what I need to do is I need to cast the old top to the new top and the timestamp to the new timestamp to return it. Now, there's a funny thing here. Let me back up a minute. Notice what new top is. New top is 0. Okay. And the reason new top is 0 is because we're only going to do that cast if we're fighting for the last unit of work. And if it's the last unit of work, we might as well set the top and the bottom to 0 again, right? Because it's empty. So that's the way that works. So here we set the bottom equal to 0 and we cast it. And failing that, we're still going to set the new top to the new stamp. And the slides mess up here because I think it doesn't set bottom equals 0 in this case, which it needs to do if it's going to reset the queue. Okay, so right, so that's where it took the work. And if it loses, the thief must have won, right? And if it failed, then you still have to reset. Okay, so does that all make sense?
I think the idea makes sense. It's just like the code, I have to look at it.
Yes, you have to stare at the code long and hard. There's no question about that. It's like anything else in this course, the code kind of makes sense when you first hear it, but really knowing if it makes sense, you have to run it even, I think. Okay, so there's this old English proverb that says you may as well be hanged for stealing a sheep as a goat, from which you can conclude that stealing was punished severely and that sheep were more valuable than goats. And the message is that stealing is expensive. And if you're going to pay cash and you only take one thread, that seems like a poor trade-off, right? So what if you randomly balance loads? So there's another concept that we have called work balancing, right? Where you can do the following. So you go and you get your task off your queue. And then if the task isn't null, you run it. And then you can look at the size of the queue and randomly, if you get next int of size plus 1 equal to size, then you select a victim, some other queue, and then you find a minimum and maximum. So then you get the minimum and maximum of your thread ID and the victims, and then you lock both in, canonical order. And then you can call this balance method. And the balance method will adjust it so you both have the same amount of work. And with work stealing and balancing, you have a clean separation between the app and the scheduling layer. And that works well when the number of processors that you need fluctuates. And it allows you to treat the operating system as sort of a black box, right? You've just got a bunch of tasks and a bunch of workers, and you try to keep them all busy. And that's the basic logic. And, you can imagine the tasks being letters such as Tom, Marvolo, Riddle. And when they come out, they could come out in a different order and they could spell I am Lord Voldemort. This used to have a nice animation, but it somehow broke over the years. All right. So, hold on. I want to show you something. And I want to open IntelliJ for this. So in front of you, what you see is a code for uh, running the Fibonacci problem, right? And the way this code works is first I get this executor service, and I'm going to get a new fixed pool thread pool of 400. And that seems like a big number, right? Because I probably don't have 400 cores, right? But there's a reason I did it. All right, and then I'm going to have my Fibonacci method, which is going to be called fcall. And what's going to happen is I have my base case, right? If n is equal to 2, why did I not get... Oh, it's over there. Hold on. Let me switch over to chapter 16. Okay, so what's going to happen is in my base case, I'm just going to return it immediately. Otherwise, I'm going to submit, and then I'm going to just, and what I'm going to submit is a callable that just does fcall of n minus 1, right? And then for for the second value, I'm just going to call it directly. So I'm going to start this one in the background, and I'm going to run this one in the foreground. And then I'm going to say f1.get plus fn2 is my value for Fibonacci, right? So that's making, using the current thread and some different one. Oops. And then I have a main method, which, I run that goes from 0 to 45, and it attempts to compute the Fibonacci numbers. And then when I'm done with that, I shut down my executor service. So that looks great. Jeez. That looks great, but eventually it blocks. In fact, it only gets up to Fibonacci 15 or so, because every time I call that block, I wind up blocking another worker in my queue. And after about Java 15, Fib 15, it just stops working. At least when I first ran this, it did. And then, so another way I can do it, right? What did I improve here? Yeah, I used a fork join pool instead, which seems to work a little better. And in fact, it does even succeed in getting to fairly large numbers, but there's a problem. There's a problem sort of hidden here, and so let me switch over to my code, and we go to fibexec2. Okay, so here's the code that I have. Now, if I run fork join pool, I think it works reasonably well. But I think that fork join pool is like hiding things from us, and we'll delve into that in a minute. So let's see how this goes. Right. So it seems to be running right along. But I think it's being tricky. And let's back up and take a look at things in more detail. And the way we're going to do this is, rather than using one of the built-in pools and just trusting it to be, magically great, we're going to make our own. So we have my executor, right, which is going to implement executor service. And I made something that does this. And so my executor service is going to take a bunch of these decks that we just figured out how to make. And it's going to make an array of n of them, right? Whatever I got in my constructor. And then I'm going to set it up so that they're continuously running and getting work. So they try to call pop bottom, and if they get null, then they try to call pop top on another thread. And if they can get a thread, then they're going to run it. And then I'm just going to get all these things together, and I'm going to set daemon and start them. And I have a simple queue, which the difference between a simple queue and a deck that we saw is that the simple queue is designed so that any number of people can insert work on it. The pop bottom and pop top and pop bottom are all going to work designed with synchronized in mind. They're all going to work concurrently like that. And I did that because that simplifies the use of the main thread. So the main thread can just submit to the Q0, and Q0 is less efficient than the others in principle, but that's okay because we're just doing a basic thing for a class. All right, does it make sense? Are you with me? Okay, good. So that starts up all the workers. I have a method to get a queue, to get a queue, and so this queue thing is a thread local queue, right? So if you have you can get the whatever your current queue is that you've stored, or you can get Q0 if you don't have one on your thread. And then basically what's normally going to happen is you're going to get your queue and you're going to do a push bottom on it to submit work. Never mind this other part for now. There's a shutdown method which I've implemented, but the important thing is the push bottom and the pop. So the workers are going to be popping, and the threads themselves are going to be pushing, and that's going to be basically how the whole thing goes. There's a submit is going to be put a callable task in there. It's going to get a future back, and it's either going to set a result or set an exception on there. And most of the other methods on the class, I just have them throw unsupported exception because we really don't need them for what we're doing here. So I just have them do nothing. I did have to implement my own future to make all this work the way I wanted to. So the future is going to know what its execution service is. It requires that it has one. It's got its core thing that it's going to do is it's going to what it's normally going to do is it's just going to sit in a while loop. Okay, so ignore all this take side jobs thing. It's normally while the thing is not done, it's going to sit and spin in place on thread yield. Okay, and that's basically how it's going to work. It's just going to say what it's going to look at its Boolean done flag, and when you do a get, it's going to spin on waiting for that to become true. Okay, make sense? Does it make sense to everyone? All right, it's pretty simple at this level, but I'm asking you to as I say, ignore the stuff in the take side jobs. It's while not done, yield. And I have take side jobs set to false, and I have in my executor, I have blocking detection false. Okay, and I have a queue size of 1,000. So we did this for fixed size queues, and we did it for we're going to set that queue to a size of 1,000. So let's go to fib exec 2 and run it and see what happens. We got up to fib 6 before it blocked. Great. That's not what we wanted, is it? Okay, so the thing is that we can do, right, is we can fix it. One of the ways we can fix it is with this thing that I call take side job. So I'm going to set that to true. And this is going to allow a value of 1,000 in the side job count thing. And what is going to happen is if take side jobs is enabled and I go into this loop and I'm not done, what I'm going to do is I'm going to take this side job counter and I'm going to get it. And if it's greater than 0, then I'm going to decrement it by 1. And I'm going to get my executor out. I'm going to get another task. I'm going to call pop, and pop is going to either call pop bottom or pop top. It's going to just sort of figure out which it can get, where it can get a task. And then if it gets something, it's going to run it. So instead of just sitting there doing nothing when you call get and the task isn't done, it's going to try to help out by pulling a task off a queue and running it. And if I enable this, I got up to 24. That was better than 6, right? Still not ideal, but I got up to 24. That time I got up to 23. So there's a certain amount of randomness in here. Now, what I could do, I have 1,000 up here, right? I could make it bigger. I could say, why not let it do more than that? Let's give it 10,000. Let's try that. And now, oh, now we run out of memory, run out of stack, right? So we kept calling things, in an effort to help things out, we kept calling methods, and we ran out of stack space. So that didn't quite work out the way we hoped. Let's put that back to 1,000.
Way to avoid that and keep the high side job count.
Well, no, because that's the problem. Once the high side job count allowed you to overflow the stack. So
We have left. Offline.
there might be, but what we're going to do instead is we're going to take a look at, we're going to go over to the executor here, and we're going to take a look at, we're going to enable the thing I call blocking detection. Now, what this is going to do is it's going to figure out, it's going to keep track every time I run a task of how many work queues I've blocked with going into get like I've done. And if I only have one thing left, right, then what it's going to do is instead of submitting a job to the queue and running in parallel, it's just going to run it sequentially. Remember, we talked about the executive service being like a New England traffic sign. It's advisable. Well, if I have blocking detection on and I have too many blocked threads, then I'm just going to run the command directly. I'm not going to try to run it in parallel. I'm just going to run it because I'm out of parallel workers. They're all busy waiting, right? So I'm going to just do that. And now, look at that. It's running. But probably most of this time while it's running, all but one of those workers is sitting there blocked because, because we have, and what's the fundamental problem here? Why is all this badness happening to us? Why do we have to fight so hard with this? What is the fundamental reason that things are the way they are? Well, that isn't actually the problem. Having much more tasks than workers is a good thing. It means you have opportunities for parallelism, but we aren't able to make use of the parallelism, and why not? Okay. Because it's a blocking algorithm. Because future.get blocks, and it's killing every one of our threads. So that takes us to fibexec3. So fibexec3 is also going to run with my executor. And the way it's going to work, so there's kind of a deficiency in the Java API that I had to sort of fudge my way around. But in order to get we want something that runs completely asynchronously is the goal. We don't want to have get. Now, it turns out that there are other things that you can call. So there is, if you use something that's called a completable future in Java, they have a then except. And what then except will do is when the future is ready, right? Instead of blocking and waiting for it, you say, here's a method that you should call when that future is ready. And you pass that to then except or then run, right? Then except will actually get the value of the future for you and put it in this supplier argument here. This V will give you the result. And so they have a supply async, which can take a supplier of T and it will return a completable future of T. But what I would really like to have instead of that is I'd like to have supply async fut. I'd like to have something that I hand it a supplier which creates a completable future of an integer in this case. And I want it to pass that integer back down to me so that I can sort of chain these futures together. That's kind of what I want. And that way, what I can do is I can write a Fibonacci method that returns a completable future. If I have my base case, I return completable future.completed future. I hate these pop-ups. Or completable future.complete future, right? So it just computes it directly, sets it, its value when it creates it. F1, I can run in the background through the executor, right? And what I'm doing with this method is instead of waiting for that value, I'm saying, hey, whenever it is you finish, call this function here to compute n-1. And then F2, I'm calling directly, right? But I've now made fcall return a future because I'm trying to make this all non-blocking. And then completable future has a then combine. So I say F1 dot then combine F2, and that gives me the values of future 1 and future 2 as integers, and I can add them, and my lambda can return that value. So I'm returning, when I combine, take then combined, I'm passing in two futures, I'm getting a new future back, and that new future back is going to be the sum. You see how that works? You can all answer tough quiz questions on it now, right? Supplier is when I have hold on, let me just show you. Cool. Supplier is an interface that looks like that, right? It takes a parameter T and it has T.get. So it computes a value. All right. So but I want it to compute, instead of computing the integer that I need, I want because I'm going to want to pass it fcall and I don't want to call get, right? I want it to have, the thing I want to have back is a completable future of T. And I want a version of supply async that instead of taking a supplier of integer, I want a supplier of future of integer. So I had to write that myself, right, up here, which is what I did. So I have supply async future, and that takes a supplier of a completable future of T and an executor service. And the way that works is, first I create a completable future of the correct type. And then I do a run async of the completable future. And run async is going to call this lambda method for me. And this lambda method isn't going to return a value, but what it's going to do is this is going to run this method after the future is ready. So when I call supplier.get here, it's not going to block, right? And then but the thing that it gets back is a future. So I'm going to call then accept on that future. And that will take the value out of that future, pass it into V, and set the result on this variable that I declared out here. So it's a little convoluted, but the net effect is that I can pass, instead of passing something that returns a T to the thread pool, I can pass something that returns a future of a T, and the T will just migrate through all the futures until it gets to where it needs to be. You make sense? Okay, so what I want to do, right? I want to eventually get a future. So let's say n is 10. All right. In F1, what I want to do is I want to compute the Fibonacci of 9. So I'm going to have to call fcall of 9. But fcall of 9 actually doesn't compute the Fibonacci number of 9. It computes the future of the Fibonacci of 9. And it's actually that future of the Fibonacci of 9 that I want in F1. So what I'm going to do is I'm going to arrange things so that when this function finishes and that future is value is ready, it sticks it in another future. And that other future is the one that I return from the supply async future method.
So it's kind of putting the result in storage.
Yeah, so I create a storage place for this result, and then when it's ready, I stick it there, right? And so that allows me to call this method through the thread pool. Okay, I don't know why Java didn't supply that method. It seems like something that I would always want, but anyway, I wrote my own. Yes, well, so for 10, I'm doing that in the background for 9, right? But for 8, I'm just calling this directly, right? Yeah, well, every time I call future, I'm going to take one of the two Fs and I'm going to compute it in the background. And then I combine, and at the end I combine them, right? Yes. But the net effect of this is I never block. The only place I'm calling get is here, and that's harmless because I know the future is ready when it gets called. All right. So, right. So then what I'm going to do is then I'm going to try to run this, and I'm going to time it, and I'm going to use fcall.join. Join is like get, except it doesn't throw an exception. It's just nicer. And now let's go back to our executor service. Wrong, not where I wanted to go. I wanted to go to, where am I? I did not want to be there. Let's go to my executor. All right. Let's turn off blocking detection. And let's go over to my future. And let's turn off take side jobs. And now let's go over here and run that. And it just runs. Right? So the lesson is, right, even though you can sort of fight with the system and make it work with blocking methods are secretly hurting you whenever you use them. And if you can rewrite everything in terms of non-blocking methods, chances are you'll be better off. Now, there is an optimization here, which I didn't do. It's kind of a basic thing that you want to do whenever you do any parallel computation. And that is, you don't want to do too little work inside a single task, right? And if I'm calculating things like Fibonacci of 10 or less, that's a trivial amount of work, right? It takes me almost no time at all. And I really shouldn't be doing work in units that's that small. So I have Fibonacci 4, FibExec 4, which if I could double click, all right, so in Fibonacci 4, I have basically the same code, except in my fcall method, I have if n is less than 23, completable future.completed future fcall sync. And fcall sync is going to compute Fibonacci directly. Now, there's something else that I changed in Fibonacci 4 over Fibonacci 3. Did anyone spot it? Besides this additional call to fcall sync, do you see what's different?
And less than 2.
Well, that was there before. So here's Fibonacci 3. Right, so if n less than 2, that's there. Look at F call. What is different? F3 to F4. Why can't I double click? There we go. What's different? Do you see it? A long instead of an int. And the reason I do that is because when I run it, I'm getting up to much bigger Fibonacci values, and they don't fit in an int. So if I hadn't done that, then by now you'd start to see negative numbers for your Fibonacci values. So I switched it to a long. So, okay, so that's one of the other lessons there is try to not do too little work in a single thread, right? You have to put some intelligence in there to try and in whatever you're doing to try and not divide the work into too small pieces. When I was a graduate student, I had this black hole code, that simulation code that I ran, and I became a postdoc, and we went to a new place, and they had a new computer that allowed you to run in parallel. And they had a magic compiler that would parallelize your code for you. And I thought, oh, cool, I'll try that. So I ran it, and my code was slower. And the reason it was slower was because all this complicated physics loops that I had, it looked at those and it said, I don't know what to do with those. I can't run those in parallel. And then I would do things like have an array of 10 things that I was putting to zero and say, okay, I can run that on 10 threads, right? And it added so much overhead for those threads for that tiny amount of work that it was counterproductive. So the automatic parallelization feature went away, and I don't think anybody has one currently. I think that's just an abandoned dream at the moment. So, I mean, I'm sure there are people who've got things that work to some degree, but it's in general, automatic parallelization is too hard to be handled automatically for you. So, all right. So that tells you basically how you can run Fibonacci in parallel. Now, as usual, our book is flawed. Now, I showed you this wonderful algorithm for the deck, and I made it for you here. Okay, and it's basically everything that was in the book, the way it was, except of course it's got this bottom equals 0 that the book forgot, right? Or the slides forgot anyway. I can't remember if the book did. And when I run it, I have a test method on here. Shoot, where's my test method? I need to remember. It's probably on worker. Yes. Yes, it's worker. Okay, so I have worker here, and I can run worker, and what I get is an exception. Great. What did it tell me? Runtime exception, task count mismatch. So that said the total tasks I gave it and the tasks that it actually ran didn't match, right? It didn't run them all. What's going on? What's wrong with this method? It happens frequently. Now, to be fair, it took me a while to get the right parameters for the queue to make it always fail. But it always fails. And why does it fail? Okay, I got 3 threads, okay? And I'm testing it a bunch of times. When I run the test, inside the test, I create a bunch of workers, I start them, I join them. And then I have this thing that runs a check on them, right? And then there's a thing that does a reset. And I have R size and Q size. So this is the size of the queue that I'm working with, and R size is the number of tasks I give it, I think. Let me look and see. Yeah, so inside my run loop, what I do is the first time it runs, I get a random number of tasks. So like if I pass it 100, it might give me 30 or it might give me 50. It just gives me some chunk of work to start off with. And then it changes this run size to 2. So from there on, it will either give me 0 or 1 tasks that are new. And for everything in this num, it's going to add a new task, except unless the queue is full. So as while the queue is empty, it's going to keep pushing tasks on there. And then and it's going to tell the task what its work, a worker ID. And then we go through the pop bottom, pop top things that the queues normally do, right? So every time it takes a trip through, it's going to maybe put a new task in, then it's going to try to pop a task out from somewhere and run it. And because it's only generating tasks half the time, it's eventually going to run out. So the bigger I put my R task and my queue, the longer it's going to run. And the bigger my queues are, the longer it's going to run. And at this thing, I gave it 200 units of work to start its random thing with, and I gave it a queue size of 200. Now I'm going to change this queue size to a different number, 127. Worked perfectly. Worked perfectly. Let's make this an 8. I don't know if this is going to work the way I want it to. I know if I run this enough times, it will fail for 128. I'm not seeing it happen now, but trust me, if I do this enough times, it will. What's going on? Why is the queue size of 200 bad? Why is the queue size of 127 okay? Anybody have a thought? What in our algorithm depended on the size of a byte? It took me the longest time to figure this out.
The size of a byte, but I don't know
What that could possibly have to do with anything? Okay, so here's another code I'd like to show you. So what does this code do? It takes an atomic stamped reference, right? And it goes from I0 to I100, I100 to I200, I200 to I300. And these are all stored in ints, right? These are just names of values, right? All right, so let's run this code. Nothing could be more innocent than this code, right? It's not even running in parallel. And it should say true, 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 right? First, I change it from I0 to I100, then I100 to I200, then I200 to I300. How can it possibly fail? Didn't I set it to the same exact value?
Well, if you're using bytes, then no.
But I'm not, right? I'm using ints.
See why it would be no, but
Calvin, do you have any ideas? You took 1351 from me. You have to dig back in your memory, I guess. The answer was given in 1351, but maybe you don't remember. What do you mean? What's wrong with it? Okay. Let me show you another code. Okay. Let's run this code. It works.
Yeah. But,
Look,
so
it's an int.
Your class. So it wasn't putting a reference, it was putting a number.
So the point is, right? When you see this compare and set, because you're a human and you know that the type is integer, you're imagining that what the machine is looking at is the integer value. It's not, right? Integer is an object. And when it's comparing the reference, it is comparing the machine address of where that integer is stored in memory, right? And because Java is trying to be helpful, it automatically converts between ints and integers for you. So in the check code, whoops. Come on, I can hit it. There we go. So in the check code, what happens is I have an int. So Java has to invent an integer object for each of these values. Now, how does it invent integers? Well, what it does to try to be optimized, it keeps the first 128 values, 0 to 127, it keeps those in a table. And if you want those integers, you just look them up from the table. If you want the integer value of 17, it's the 17th thing in the table. It always gives you the same object. If your integer is outside of that table, it allocates a new integer object every time. So what happened is, right, the first one worked because it was pulling 100 out of that table. 0 and 100 both came out of that table. But when I went to get the 200 is a new integer with value of 200 every time. And so this 200 and that 200 are at different locations in memory, and it fails. It really is. It's really awful. It's one of the biggest mistakes in Java, in my opinion, is this whole integer autoboxing thing. And this is why the queue fails. So it turns out that fixing it is quite straightforward once you know what the problem is. So look at what we have here, right? We have int old top.getStamp, right? Now, stamp is fine because that's truly an int. That's not an integer. So the stamp is fine. But this isn't really an int. If I just change int to integer everywhere, right? Then it works. It took me so long to figure that out.
How do you begin to figure that out?
If you have like a big enough program where it's like you wrote this code like 3 years ago and you're now like
Yeah. Imagine how horrible this could be. No, the way I figured it out, right, is as I kept writing tests and the tests kept failing. And I was like, I eventually realized that 128 was a magic value. And once I knew that, and I was looking and I knew that and I saw the values from my printouts and the thing failing. And then I began to see, oh yes, compare and set of 200 to 200 doesn't work.
this is one of those things where it's like, yeah, so probably right.
But when I teach 1351 and when I teach this course, I bring up this point because it rarely ever shows up when you're programming, but when it does, it really ruins your day. And you have to be ready for it at least somewhere in the back of your mind. So you should always be aware that Java can play this nasty trick on you. But again, fixing it is so easy. And of course, the authors of the book didn't catch it, right? Because they just didn't test it the right way. If they tested it with probably a Q of a size 100 and then it worked perfectly.
The problem was that like it wasn't getting any new items from the queue.
Yeah, well, the problem is these compare and sets were failing for everybody because they were allocating new integer objects and it didn't match. So it couldn't get the object out of the queue. It was so that's why it doesn't work. And the error is for you to think that that the computer sees integer as a value and not a machine address, and it sees it as a machine address. And that's the fundamental problem. Okay. I think that might be everything I wanted to say.
Are we done with chapter 16?
Yeah. So this is what always happens to me is I finish all the slides in the first of the two lectures, and the second of the two lectures we have questions and we have homework and we have other things of that nature. I would like to give you a homework. I haven't decided exactly what it is yet. I'll try to get it done, get it in by tonight.
When is it?
I typically give you a week. If that doesn't happen, so the next class we will talk about these things some more. I have a couple other things I can show you in related to this, but it won't take up a full class. If we have questions and we have a quiz, it might all work.
Be sure to
Be sure to come with a lot of questions. Otherwise, I'll proceed to the next topic. All right. Any other questions for today? All right. All right. Stare hard.